Today, the solar system consists of 8 planets, namely Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. All these planets revolve around a massive ball of helium and hydrogen known as the Sun. There are other bodies within the solar system, such as moons that revolve around the planets, asteroids, and planetoids. Jumping ahead in time, the systems of 3 astronomers were prominent in Kepler's day around the turn of the 17th century. They were Claudius Ptolemy, who developed the mathematics for an Earth-centered planetary model in the 2nd century AD. Nicolaus Copernicus, who is famous for introducing in modern times the idea that the Sun is in the center of the planetary system. And Tycho Brahe, a well-to-do Danish nobleman who understood the importance of advancing the observational techniques behind astronomy if the science was to truly progress. These 3 astronomers each created systems to understand the motion of planets which, at first glance, appear very different. Let's have a look.
I will be discussing the comparison and contrast of the explanations and models popularized by Copernicus. Copernicus is widely known for his groundbreaking model of the universe, which placed the Sun at the center and the Earth and other planets orbiting around it. His model challenged the traditional Ptolemaic system, which held that the Earth was the center of the universe. In this discussion, we will explore the key differences between these two models and the explanation they provide for the movements of the planets. First, let's examine the Ptolemaic model. According to this model, the Earth is at the center of the universe, and the planets and stars orbit around it in perfect circles. To account for the observed motion of the planets, the Ptolemaic system employed the use of epicycles, small circular orbits within the large orbits of the planets. The Ptolemaic system also assumed that the planets move at a constant speed rather than accelerating or decelerating. On the other hand, Copernicus proposed a heliocentric model with the Sun at the center of the universe and the planets orbiting around it in circular orbits. This model eliminated the need for epicycles, as the observed motions of the planets could be explained by their orbits around the Sun. Copernicus also suggested that the planets move at the varying speeds in their orbits, which explained why they sometimes appeared to move backward in the sky. One of the key differences between these two models is their assumption about the nature of the universe. The Ptolemaic system assumed that the Earth was the center of the universe, with all other celestial bodies orbiting around it. Copernicus, on the other hand, proposed that the Sun was the center, with the planets and stars orbiting around it. This fundamental difference in perspective had significant implications for how astronomers understood the movements of the planets and the structure of the universe. In conclusion, the Ptolemaic and Copernican models represent two very different ways of understanding the movements of the planets and the structure of the universe. While the Ptolemaic system relied on complex and convoluted explanations for the observed motions of the planets, Copernicus' heliocentric model offered a simpler and more elegant solution.
Although Copernicus' model was initially met with resistance and controversy, it eventually became widely accepted, paving the way for future advancement in astronomy and our understanding of the universe.
Now let's talk about Tycho Brahe. Tycho Brahe was a renowned astronomer in the 16th century who made significant contributions to the field of astronomy. He is known for his observations and precise measurements of celestial objects, which were instrumental in the development of modern astronomy. In this blog post, I will be discussing to you the astronomical phenomena that Tycho Brahe popularized and the model he used to explain them. And now let's move on to Tycho Brahe's model. Tycho Brahe's model was a hybrid between the Ptolemaic and Copernican models of the solar system. According to the Ptolemaic model, the Earth was at the center of the universe and all celestial objects orbited around it. However, the Copernican model suggested that the Sun was at the center of the solar system and all planets including Earth orbited around it. Tycho Brahe's model, on the other hand, suggested that the planets orbited around the Sun, but the Sun orbited around the Earth. This model was known as the geoheliocentric model, which means that the Earth was at the center of the universe and the Sun and other planets orbited around it. And now I will show you the astronomical phenomena of Tycho Brahe. Tycho Brahe was able to explain many astronomical phenomena using his geoheliocentric model. One of the phenomena he explained was the retrograde motion of planets. Retrograde motion is the apparent motion of a planet in the opposite direction to its usual motion across the night sky. Tycho Brahe explained this by suggesting that when the Earth and a planet were on opposite sides of the Sun, the planet would appear to move in the opposite direction as seen from Earth. Another phenomenon that Tycho Brahe explained was the apparent size of the Moon. He observed that the Moon appeared larger when it was closer to the horizon than when it was high in the night sky. Tycho Brahe explained this by suggesting that the Earth's atmosphere acted like a magnifying glass, which made the Moon appear larger when it was closer to the horizon. Tycho Brahe's contributions to the field of astronomy were significant, and his geoheliocentric model and explanations of astronomical phenomena were groundbreaking. His precise measurements of celestial objects and his observations of the night sky paved the way for the development of modern astronomy. Although his model has been largely superseded by modern models of the solar system, his contributions to the field of astronomy are still highly regarded and celebrated today.
The Ptolemaic model, known as the geocentric model, was developed by an Egyptian astronomer Claudius Ptolemy. It came from the Greek word geo, means earth, and centric means center. This model explains that the earth is the center of the universe and everything else revolves around it. Each planet moves in a circular path called apical, which moves around a larger circular path called deferens. The moon revolves around the earth, followed by the other planets. As the stars move overhead during the night, the image of a sphere is inescapable. Based on the idea that the stars were on a larger sphere, Ptolemy stuck the Earth right in the middle of it, held in place by all the air out there. We don't feel the Earth move, and there's nothing stiller to find in our experience than the ground itself. So Ptolemy thought that all of the stars move around the Earth every single day, and the proper motion of the sun, moon, and planets was added to that common first motion of the entire heavens. You may be wondering or asking question, couldn't the Earth be at the center of the universe and still spin? Wouldn't that make things easier? Well, no, that wasn't possible according to Ptolemy, because then if you jump in the air or fired an arrow, the earth would spin out from underneath it, and you and your arrow would land in another continent. Here's what Ptolemy wrote about the earth moving in space. So let's see.
And if the earth had some uncommon movement, the same as that of the other weights, it would clearly leave them all behind, because of its much greater magnitude, and the animals and the other weights would be left hanging in the air, and the earth would very quickly fall out of the heavens. Merely to conceive such things makes them appear ridiculous. For us to grant these things, they would have to admit that the earth's turning in the swiftest of absolutely all the movements about it, because of its making so great a revolution in a short time, so that all those things that were not at rest on the earth would seem to have a movement. Contrary to it, and never would a cloud be seen to move toward the east, nor anything else that flew or was thrown in the air, for the earth would always outstrip them in its eastward motion, so that all the bodies would seem to be left behind and to move towards the west.
Now, back to the planets. Remember the loop that we saw the planet making the motion over time? How could Ptolemy account for that? Well, instead of the planets simply moving around the Earth, Ptolemy added the second circle as well. The first circle is called deferent, and on its spins as epicycle or an epicycle on which the planet itself is seen. With this epicycle, Ptolemy accounted for the loops made by the planets. As we grow the epicycle to the appropriate size, it makes the apparent loops the planet trace out and even makes the planet come closer to the Earth during the loopings. And indeed, Mars appears as it is brightest during the backward motions. Now, while the model you see here has a specific size for the orbits and a physical in order for each planet to have its own sphere, Ptolemy's mathematical astronomy work didn't actually include those distances, since he only cared about where you'd see a planet and not where it actually was. He was gave ratios between the orbits and the physical for each planet.
He is most known for refining the cycles and epicycles that made the geocentric theory for the universe tenable for 14 centuries, as established in his book The Almagest of the Motions of the Planets and Stars. This is the theory which Galileo Galilei and Isaac Newton eventually overthrew more than 1,000 years later. For this reason, Ptolemy is a controversial figure in the history of science. Newton says that the Ptolemies simply fitted his measurements to his theories rather than vice versa, often adopting observations made centuries before his time.
The three models and explanations share similarities, such as their ability to explain the retrograde motion of planets. However, their fundamental differences lay in the placement of Earth and the Sun in the solar system. Copernicus' model places the Sun at the center, while Ptolemy's model places the Earth at the center and Brahe's model is a hybrid of the two. Furthermore, Copernicus' model is simpler and more elegant than Ptolemy's model, which required the use of epicycles. However, Brahe's model attempted to combine the best of both models and provided more accurate measurements of planetary positions. In conclusion, the models and explanations of astronomical phenomena proposed by Copernicus, Ptolemy, and Brahe all contributed to the development of modern astronomy. While Copernicus' model has proven to be the most accurate and is widely accepted today, Ptolemy's model and Brahe's model were significant in their time and helped pave the way for further advancements in the field. The study of the universe and its workings is an ongoing process, and each new model and explanation adds to our understanding of the cosmos.